Britain's best-loved soap opera Coronation Street is just finishing.
Would you like a cup of tea?
Yes, please.
At the end of that programme, there's a sudden surge in demand for electricity as kettles all over Britain are switched on. How is all that extra electricity suddenly made available?
Dynamic National Control here. Could you generate 240 megawatts on number 2 machine, please? Thank you.
Believe it or not, there's a power station in this mountain. That's where the extra supply comes from. The power station can be switched on and will generate full power within 15 seconds. But it's the only one of its kind in England and Wales, and it's only ever used as a last resort when there's an exceptional need to provide extra power for a short period of time. Think of the millions of homes in Britain. Then think of all the things in those homes that use electricity. Where does all the energy come from? Generating a little electricity is simple enough. When a magnet is introduced into the centre of a coil of wire, an electric current is induced in the wire, but only for as long as the magnet is moving. When the magnet is withdrawn from the coils, current is induced in the opposite direction. The faster the movement of the magnet, the bigger the current in the wire. If the magnet is moved rapidly in and out, the current keeps changing direction. It's an alternating current. This equipment is a simple generator. Generating electricity is all about converting energy from one form into another. Here, kinetic energy, the movement of the magnet, is being converted into electrical energy in the wire. The electricity that we use in Britain is supplied from more than 70 power stations. They all have generators on a grand scale, which convert kinetic energy into electrical energy. Where does the kinetic energy, the movement, come from? It comes from a turbine, which is basically a wheel, which will turn when energy is applied to the blades. In most power stations, the energy is supplied in the form of steam. This apparatus demonstrates the principle involved on a small scale. It's a miniature power station. The steam produced by boiling the kettle is directed at the turbine. It strikes the blades and makes the turbine rotate. The turbine drives the generator, a magnet moving in a coil of wire with many turns in it. An alternating current is generated. Notice the change in direction of the needle. More than 70% of our electricity is generated at power stations, which use coal as fuel to make steam. Coal is one of the fossil fuels, along with oil and natural gas. This is one of the biggest coal-fired power stations at Fiddler's Ferry near Warrington in Cheshire. The delivery train moves slowly through the discharge area without stopping. The coal falls into underground hoppers and is carried by conveyor belt to the coal store. The coal is already in small lumps, which makes for easier transportation and handling. A stockpile is kept in case of any disruption to supply. There are more than 400,000 tons here at the moment. The coal is crushed into very fine powder in these pulverizing units. That's done for two reasons. The smaller the pieces, the greater the surface area available for reaction during combustion. It also makes the fuel easier to handle. It can be blown with hot air as a fine powder through pipes and into the boiler furnace. In the furnace, the fine coal burns like a gas. All fossil fuels release energy when they are burned, combining with oxygen to produce a lot of heat, as well as some waste materials. The heat is absorbed by water contained in many kilometers of coiled tubing, which form the boiler wall. The water is turned into steam at high pressure. This is where the next stage of the process happens, the power hall. The blue machine is the massive equivalent of the little turbine of our demonstration. The steam from the boiler goes into a high-pressure turbine. It turns the turbine, but in doing so, gives up some of its energy. So it is fed back into the boiler to be reheated and used again to turn a low-pressure turbine. The orange machine is the generator. Inside the generator, linked to the turbine by a shaft, is the rotor, which is actually a large electromagnet. It turns at 3,000 revolutions a minute inside the stator, which has many coils of copper wire. The generator produces electricity at 22,000 volts. The power output of each generator is 500 megawatts, and at Fiddler's Ferry there are 4 of them, giving a combined total output of 2,000 megawatts. Once the steam has done its work and exhausted its useful energy, it has to be turned back into water so that it can be reused. That happens in the green pipes, which are the condensers. The water in the boiler system is very pure. It has to be like that to minimize any problems with corrosion in the pipework. The water in the cooling system is different. It's poor quality, so it's kept separate. A heat transfer system operates in the condensers. The steam from the turbines turns to water as it gives its heat to the coolant water. The coolant water is then pumped away to the cooling towers, which are a familiar sight at coal-fired power stations. The water is pumped in at around 15 meters up the tower. That's only a quarter of the way up. The height of the tower creates a powerful upward draft of cold air. The water is sprayed out through a sprinkler system. It is cooled by the cold air as it falls to the reservoir below. Often people think that the output of a cooling tower is pollution in the form of smoke. In fact, it's only steam. Around 30,000 gallons of it is given out every day. But there is a lot of heat going up into the atmosphere. Any water lost through evaporation in the cooling towers is replaced with water extracted from the nearby River Mersey. Let's look now at a nuclear power station, and there's an immediate difference from the outside. There are no cooling towers. That's because most nuclear power stations are built next to the sea or an estuary. This wheel filters the seawater to remove debris before it's used in the condensers as a coolant for the turbines. It's discharged back into the sea after it's been used. The turbine room, though, is similar to Fiddler's Ferry. In fact, the turbines and generators at the 2 power stations are almost identical. It's the method of generating the steam that's different. This is the reactor hall at the Heysham Nuclear Power Station in Lancashire. It's the equivalent of the boiler house at Fiddler's Ferry. There's a fuel involved here, but no combustion. The fuel is uranium dioxide. It contains a radioactive isotope which can be split to release huge amounts of energy. This is the top of the nuclear reactor, and all the action takes place under here. In the process, the atoms of the isotope uranium-235 are bombarded with neutrons. The nucleus splits into 2, and a great deal of heat is given out. The heat is used to make steam in the boiler. The fission, that's the splitting of the nucleus, causes other neutrons to be released. Those neutrons then go on to collide with adjacent atoms of the isotope, and further splitting happens. When fission takes place in a series of atoms, that is called a chain reaction. In the nuclear reactor at Hisham, the fuel is in the form of pellets of uranium dioxide. The pellets are put into steel cans, which are then linked together to form a fuel element. 8 elements in line make up a fuel assembly. The fuel assemblies are surrounded by a graphite core, which is essential to the process. Nuclear fission, the splitting of the atoms, happens within the fuel assemblies. The graphite slows down fast neutrons that are released by fission. This makes them more easily absorbed by other atoms, so that a chain reaction occurs. If the chain reaction was allowed to go unchecked, the consequences could be disastrous. The heat would build up until the reactor melted. So a control mechanism is built in. The reactor core also houses control rods made of boron. Boron is capable of capturing fast-moving neutrons and absorbing their energy. So the rods can be raised or lowered to control the rate of the chain reaction. The heat from the fission is absorbed by carbon dioxide gas, which circulates through the reactor. For this reason, it's known as an advanced gas-cooled reactor. The heated gas passes over coiled tubes containing water, which is changed into steam. Once again, steam is used to drive the turbines. The generating process is then almost identical to the one at Fiddler's Ferry. Hisham produces up to 1,320 megawatts of electricity from its 2 reactor units. It's altogether a cleaner process than at a coal-fired power station. No dust, no smoke. But both systems have their disadvantages. Can you think what they might be? One of the major concerns with both ways of generating power is over waste and its effect on the environment. With nuclear power generation, the problem is how to dispose of the products of the nuclear fission process. They are highly radioactive, and radiation is dangerous to all life. The fuel itself is always in a closed system. Before, during, and after nuclear fission, it's managed by machines in enclosed areas. Movement of materials within the system is monitored on TV screens. This is the top of a fuel element. You can see the 36 steel cans which hold the uranium dioxide. Most of the fuel has been used up, but what's left is still highly radioactive, so it's moved by remote control to a storage pond. The pond is full of water, which is a sufficient barrier to contain the low level of short-lived radiation that is given off. The used elements stay there for 100 days. At the end of that period, the spent fuel is judged to be safe enough to be moved to another location. Radioactive waste is extremely difficult to dispose of safely. It'll be radioactive for hundreds of years, so has to be kept in long-term storage. The handling and disposal of nuclear waste is one of the most controversial aspects of nuclear power. As for waste from coal-fired power stations like Fiddler's Ferry, it has its problems too, mainly to do with pollution of the atmosphere. Coal contains small amounts of compounds of the element sulfur. When the coal is burnt, the sulfur is oxidized to become sulfur dioxide. Sulfur dioxide is a serious air pollutant which helps to cause acid rain. Coal-fired power stations account for nearly half of all the sulfur discharged into the atmosphere in Britain. Treatment of flue gases can help to reduce the amount of sulfur dioxide released. The other problem is with the main gas produced in combustion, carbon dioxide, which has been linked with global warming. It can't be removed from the flue gases. The only way for us to reduce emissions of carbon dioxide is to cut back on the burning of fossil fuels. There is another problem with power stations, and it's less obvious. It's been estimated that for every 100 units of energy that is put into the power station, energy stored in the form of coal and oxygen, only 35 units comes out at the other end of the process as electricity. An enormous amount of energy is lost in the system. Where does it all go to? Well, an obvious place is up the chimney. Waste gases are still hot when they're discharged. 15 units lost. The turbines lose some heat, but the main loss at this stage is from the cooling towers. 48 units lost. The generator loses 2 units in heat and noise. So the end product out of the power hall of the station is down to 35 units. The power generation system is only 35% efficient. It doesn't seem very good, does it? In fact, by the time the electricity gets into the home, it's lost another 3% of its efficiency. The culprit for that is the transmission system, which distributes electricity around the country. The voltage is stepped up with transformers from 22,000 volts out of the power station to 275,000 volts. Pictures taken with a thermographic camera show the amount of heat lost from the overhead cables that carry high voltage electricity. The white lines represent lost energy. But the problem with electricity is that it can't be stored. It has to be generated and used immediately, so a big distribution operation is essential. The national grid consists of several linked distribution systems at 275,000 and 400,000 volts, which serve England and Wales. Scotland and Northern Ireland have their own grids. The system is supervised from a national control centre. The sole purpose of this operation is to match supply with demand. What factors influence how much electricity is needed? The weather for a start. Cold in winter means more heating. There's more demand in daytime for power from industry. Meal times mean energy for cooking. And TV programs create peaks of their own. Daily demand can be quite accurately predicted because patterns of electricity use are well established. On a typical summer day, demand builds up to a high around noon and stays around that level for the rest of the day. In winter, as well as much greater demand, there's a much bigger peak around 6 o'clock. Hot meals are being cooked. Computers work out how many power stations will need to be in operation to meet the demand. In winter, it's around 50, dropping to 25 in summer. A coal-fired power station takes around 12 hours to reach full capacity for producing electricity. Nuclear stations require a similar length of run-up time. That's why the pumped storage facility at Dinorwig in North Wales is needed to meet short-term rises in consumption. Here it's being asked to provide 627 megawatts. The highest surge in demand ever recorded at the National Grid Centre was in 1990, after the penalty shootout at the England versus Germany World Cup semi-final match, an incredible rise of 2,800 megawatts. In the unlikely event of it ever happening again, they'll be prepared. Generating electricity is all about converting energy from one form into another. Here, kinetic energy, the movement of the magnet, is being converted into electrical energy in the wire. The electricity that we use in Britain is supplied from more than 70 power stations. They all have generators on a grand scale, which convert kinetic energy into electrical energy. Where does the kinetic energy, the movement, come from? It comes from a turbine, which is basically a wheel, which will turn when energy is applied to the blades. In most power stations, the energy is supplied in the form of steam. This apparatus demonstrates the principle involved on a small scale. It's a miniature power station. The steam produced by boiling the kettle is directed at the turbine. It strikes the blades and makes the turbine rotate. The turbine drives the generator, a magnet moving in a coil of wire with many turns in it. An alternating current is generated. Notice the change in direction of the needle. More than 70% of our electricity is generated at power stations.
Dynamic National Control here. Could you generate 240 megawatts on number 2 machine, please? Thank you.
Believe it or not, there's a power station in this mountain. That's where the extra supply comes from. The power station can be switched on and will generate full power within 15 seconds. But it's the only one of its kind in England and Wales, and it's only ever used as a last resort when there's an exceptional need to provide extra power for a short period of time. Think of the millions of homes in Britain. Then think of all the things in those homes that use electricity. Where does all the energy come from? Generating a little electricity is simple enough. When a magnet is introduced into the centre of a coil of wire, an electric current is induced in the wire, but only for as long as the magnet is moving. When the magnet is withdrawn from the coils, current is induced in the opposite direction. The faster the movement of the magnet, the bigger the current in the wire. If the magnet is moved rapidly in and out, the current keeps changing direction. It's an alternating current. This equipment is a simple generator. Britain's best-loved soap opera Coronation Street is just finishing.
Would you like a cup of tea?
Yes, please.
At the end of that programme, there's a sudden surge in demand for electricity as kettles all over Britain are switched on. How is all that extra electricity suddenly made available?